Well, hello there. Today we're going to be looking at binary numbers and comparing them. Starting with decimal numbers, here's a decimal number, 1969, 1969. This is a base 10 number. That's what we're used to dealing with. If we try to break this out into its components, so this first place here, where the 9 is the ones place. You probably remember this from grade school. Then the next place is the tens. This is the tens place with the 6. And we have another 9 in the hundreds place and a 1 in the thousands place. So this is the way we learn it in grade school with ones, tens, hundreds, and thousands. And it's important to see the pattern here with powers. The ones is 10 to the 0, base 10. Tens is 10 to the 1, 10 to the 2 for hundreds, and 10 to the 3 for thousands. So we can get our number by adding up the digits in the places and multiplying by the places. So we have 1 times 1,000 plus 9 times 100 plus 6 times 10 plus 9 times 1 gives us 1,969. And the other thing to remember is that the largest number we can store with 4 digits is 9999. And that is 10 to the 4th. So again, base 10, 4 digits, minus 1. So not 10 to the 4, but 10 to the 4 minus 1. So you'll see this minus 1 coming up when we do the binary numbers as well. And that's the reason. 9999 is the biggest number. One more than that would be 10000, but we need a 5th digit for that. So binary numbers are base 2, not base 10. With base 2, we only need 2 characters, so every digit here is a 0 or a 1. And the pattern works out the same. So we have a ones place here, the first one, which is 2 to the 0 place. The next place is 2 to the first power, so it's 2's place. The next one is 2 to the second power, so it's the 4's. Then 2 to the third power is the 8's, and then 2 to the fourth is 16. So it doubles every time because we're going by powers of 2. Base 10 goes up by a power of 10 every time. So this is the same kind of pattern, but with a different base than we had for base 10. So if we want to know what this number is in base 10, we can use the bases and the ones and zeros to add them up. So with binary, it's either in or out. So you either have it or you don't have it. You don't really have to multiply much. You're either multiplying by 1 or 0. So we have a 16, we don't have an 8, we have a 4, don't have a 2, we have a 1, and that gives us 21 in decimal. This is a 5-bit number, 5 binary digits. And the largest number we can get with a 5-bit number would be all ones, 5 ones, and that is 2 to the 5 minus 1. So the same kind of pattern as the base 10, and that's 31 as a decimal number. So with 5 bits, you can count from 0 to 31. So bits, that word I've been using a lot, that's short for binary digits. With binary numbers, in this class, we're pretty much always talking about whole numbers. You can do floating point kind of numbers with binary, but in this class, if we're dealing with binary, it's because it's at some low level where we need whole numbers, integers. An 8-bit whole number can represent numbers between 0 and 2 to the 8th minus 1, so 0 to 255. 16-bit, 0 to 2 to the 16 minus 1, hopefully you see the pattern, which is 0 to 65,535. If we're using binary numbers for storage on a computer, we often need negative numbers. And so they are still whole numbers, but if we want to have a negative number, one option would be to use the first bit, the leftmost bit here, to store the sign. So a 0 in the sign bit would be it's positive, a 1 in the sign bit would be negative, and then the rest of the bits tell us the number. So 101 is 5, so this is positive 5 and negative 5 using the sign bit representation. But we don't do that. That's easy for people, but there's a better way for computers called 2's complement, and it's a clever system. To change a positive number like positive 5 to a negative number using 2's complement, you do these steps. So first you have the positive number, then you complement it, called the 1's complement. You flip each bit. So the 1 becomes a 0, the 0 becomes a 1, 1 becomes a 0, 0 to 1, 0 to 1. So you flip each bit from 1 to 0 or 0 to 1. Then you add 1 to the 1's complement, and that gives you the 2's complement. So here's our 1's complement. We add 1. 0 plus 1 is 1, and then the rest just come down. 1 plus 0 is 1, the 0, the 1, and the 1. So 11011 is negative 5 as a 5-bit 2's complement number. The reason this is the clever way to store negative numbers is because of the way math works in a computer. If we have to subtract numbers, 10 minus 5, it's the same as saying 10 plus negative 5. And if we store our negative numbers as 2's complement and we have a way to add numbers, we can add them the same, we can subtract negative numbers or add positive numbers using the same mechanics. So if you have to design a circuit to do addition, you can also use it to do subtraction as long as you're using 2's complement for the numbers. So it makes designing a CPU easy. It's a little bit difficult for people. But you can see here we have, this is 10, 0, 1, 0, 1, 0, a 5-bit number representing 10. This is the negative 5 that we came before. And if I add them together, the one thing you'll have to remember is that in binary, 1 plus 1 equals 2, and 2 is 1, 0. So if we add these together in binary, 0 plus 1 gives us 1. 1 plus 1 gives us 2, so we write down the 0 and we carry the 1. 1 plus 0 gives us 1. 1 plus 1 gives us 2, so we write down the 0, carry the 1. 1 plus 1 gives us 2, so we write down the 0, and we carry the 1. So my mouse, some interesting things going on there. But I will skip to the next step where we have the summary here. So here's the summary. We have 10 plus negative 5, and we get this number by doing the math. It's a 5-bit system, so the sixth bit gets tossed. So because we only have 5, so like when your odometer overflows on your car, we lose the 6th bit and we're left with this. So 10 plus negative 5 gives us 5. So math works out. If you use 2's complement, you can use addition at the same way you would do subtraction. It makes it easy to design computers, and it stores just as efficiently. With 2's complement, you still have a sign bit. So if the leftmost bit is 1, that means it's a negative number. You can't read the rest of them as a positive number. You have to reverse the 2's complement process to find out what it is. But this always tells you that it's a negative number. So if you have an n-bit system with 2's complement, you can count from -2 to the n-1 power And then the biggest number you can store is 2 to the n minus 1 minus 1. So with positive numbers, you can go from 0 to 2 to the n minus 1. So an 8-bit positive number would be 0 to 255. 8-bit 2's complement, the smallest number would be negative 128. That would be all ones. And the largest positive number would have a 0 in the sign bit and all ones. And that's 127. So rather than 0 to 255, you're negative 128 to 127, and works out just fine. So that's all you need to know, and maybe a little more about binary numbers for this class. The most important thing is how to convert to and from binary, and what the concept of the number of bits means as far as how large you can count, because that number of bits is going to be a specification that we deal with quite a bit. So if you're doing a lot of conversion, your calculator will probably do it, and that's worth figuring out how to do. But otherwise, you can do it by hand. All right, I'll see you in the next video.